Hello everyone, welcome to Calc Chats 15. Today we're going to continue our graph analysis and talk more about how derivatives can connect to our original graph of f of x. So we have some new vocabulary. So absolute extrema are basically absolute minimums and maximums. They're across the entire domain. So if I'm looking at a parabola, I know that my parabola is going to continue to go up. So in this case, this parabola doesn't have an absolute maximum, but it has an absolute minimum right at the bottom because it's not going to get any lower on its domain. And then for an absolute maximum, a great example is another parabola, but with a negative coefficient. And so this parabola is going down, so this one has an absolute maximum. I'm never going to reach a higher point. So basically, it's the largest or smallest f of x value we can find across the whole domain. So local extrema are they're minimums and maximums, but instead of on the whole domain, they're across an interval. So if I can look at just kind of like a cubic function, we can see that on this interval, we have a point that is kind of higher than the others. So if I was looking, let's say, this interval right here, if I cut it off right here, this could be a local maximum because I'm really low down in this direction, and then I come up, and then I go back down. So this is kind of my highest point on the interval. And then we can easily see a local minimum right here. I see my function kind of dips down. So even though I have these low negative values and these high positive values, basically our local minimum are looking at where our function goes up, kind of stops, and then turns back around. Even if they're not the absolute maximum and minimum, they're points of interest. So we have what's called the extreme value theorem. And so basically what it says is if we have a continuous function on a closed interval, then f has both a maximum and minimum value. And so we can see this in any given continuous function. It doesn't have to be differentiable, just continuous. If we're looking at, for example, a cusp, this is not a continuous, or it's not a differentiable function, but it is continuous. And if I look on my interval, it has an absolute maximum at the endpoints. And now I can easily also see I have a local maximum at that bottom point. And even on a linear function, as long as I'm on a closed interval, I have a max and a min. So basically, this is just a guarantee of a local max and min. So this is kind of our big idea. If f has a local max or min at x equals c, so some value, then the derivative at that point is 0. And this also applies to our second derivative. And so if I'm looking at my parabolas, let's say c is at 0. That's my local min. Then if I see my slope, I can draw a horizontal tangent line. And the slope of that tangent line is 0. And so we're going to be using this information to help us find minimums and maximums of more difficult functions. And then if the derivative is equal to 0 or it doesn't exist, we call this a critical point. So we can think of, again, that cusp. The derivative does not exist at that cusp point, but it is still a critical point. That's still a minimum on our interval. So in this example, we're asked to find the minimum and maximum values of this function f of x equals x squared minus 2x on the interval 1 to 4. And so basically what I'm going to do is I'm going to look at the derivative. So my derivative is 2x minus 2, and I'm going to look at where that's equal to 0. And so I see I can factor out a 2. So x equals 1 is my critical point. So that's one point that I'm going to be testing. And then I see that 1 is actually the endpoint of my interval, and so I'm also going to be testing 4. When I'm testing for minimums and maximums, on an interval, I have to test the endpoints as well. So I'm going to be looking at x equals 1 and x equals 4. So now I found my critical point and I have my endpoints. Now I'm just going to plug in f of 1 and f of 4. So I should get 1 squared minus 2 times 1, 4 squared minus 2 times 4. Again, just back into the original function. So this is 1 minus 2, so that should be negative 1, and then this is 16 minus 8, so that is 8. And so I have a local minimum at the point 1, negative 1, because this is my lowest f of x. And then I have a max, highest f of x. So I have a local maximum at the point 4, 8. So I found my critical points, tested my endpoints, put them back into my original function, and that just tells me the local minimum and maximum. So now we have this other idea of increasing versus decreasing intervals. So if my derivative is greater than 0, we say that f is increasing. And again, this goes back to drawing our derivative graphs. When I had a positive slope, my derivative was positive. When I had a negative slope, my derivative was negative. And so if we take sorry about that. My smartboard just decided to shut itself off. All right, so going back to what we were talking about. If we find this cubic function, random cubic function, I see that it's increasing, then I hit a horizontal line, then my function is decreasing, then I hit another horizontal line, and then it's increasing again. So for increasing and decreasing, I'm still focused on those critical points, my local mins and maxes, and I'm focused on what's going on the other side of my minimum and maximum. And that actually helps us tell if there is a minimum and maximum, because if I go from increasing to decreasing, that has to be a maximum, because I'm going up and then I'm coming back down. And if I'm going from decreasing to increasing, has to be a minimum, I'm going down and then up. So we're going to look at this example. It's asking us to find the absolute minimums and maximums of the function and the intervals of increasing and decreasing. So first thing I'm going to do is I'm going to take the derivative. So I get this derivative is 3x squared minus 27. And I'm just going to factor out that 3 initially. And so when I'm looking for minimums, maximums, increasing, decreasing, I'm looking at where that derivative is equal to 0. So I'm just going to divide out this 3. So I get x squared minus 9 equals 0. You can either square root, take the 9 over and square root both sides. I like to factor this out just because it reminds me that I have 2 solutions. So I get x equals 3 and x equals negative 3. And so these are my critical points. So these are the ones I'm really focused on. When I'm dealing with increasing and decreasing, I'm going to make what's called a sign chart. And so basically these are just x values, and I put down my critical points, so negative 3 and 3. And when I'm looking for intervals of increasing and decreasing, I'm looking at what's happening beyond those 2 points and in between those 2 points. So basically I'm going to pick a value that is less than negative 3. So I'm just going to say negative 4. I'm going to pick a value in between negative 3 and 3. 0 is probably the easiest. And then I'm going to pick a value that's greater than 3, so I'm going to pick 4. And what I want to do is I want to look at these values and how they affect my derivative. I'm going to take, I ended up with x squared minus 9 equals 0. So this is kind of the last step I was looking at. We actually don't need that equals. Whoop. We don't need that equals 0. So just x squared minus 9. So I'm going to plug in -4, 0, and 4. So x squared minus 9, when I plug in -4, that's 16 minus 9. I don't even really care what it is. I just need to know that it's a positive number. When I plug in 0, I get 0 squared minus 9. That's clearly a negative number. That's -9. And then when I plug in 4 squared minus 9, 4 squared 16 minus 9, that's a positive number. So what I'm going to do is I'm going to go back into my chart, and in this section right here, I write positive because that has a positive slope. Here, when I plugged in 0 for the derivative, I got negative, so that's a negative slope. And when I plugged in 4 for the derivative, I got a positive slope. So I can already see where I have local mins and local maxes. So 3, I'm basically going, if I draw a rough sketch of my graph, from -infinity to 3, I'm going up. And then from -3 to 3, I'm going back down. And then from 3 on, I'm going again up. So I have a minimum, a maximum at -3 and a minimum at 3. And so I already have my maximum and minimums identified, and then just looking at this chart, I can tell my intervals of increasing and decreasing. So I can say F has a local minimum at x equals 3, comma, a local maximum at x equals -3. And then for my intervals of increasing and decreasing, I can say F is increasing from -infinity all the way to -3, as well as 3 to infinity. So it's increasing on those two intervals because my derivative is positive, and then decreasing in between -3 and 3. So I'm just going to write decreasing, -3, 3. So I found my local min, my local max, and then also at the same time, I found my increasing and decreasing. And if I wanted to find the coordinates of my local min and local max, all I would have to do is go back up to my original function. Oops, that's my derivative. My original function all the way up here and plug in those values. So last thing we're going to cover is just the mean value theorem for derivatives. So this basically says if I have a continuous function on a closed interval and it's differentiable on an open interval, then I have at least one point on that interval where my slope at that point, my instantaneous rate of change, is equal to the average rate of change. So when we're looking at this kind of graphically, let's say I'm going from 1 to 5, and my function is continuous. There guarantees that I do have an instantaneous rate of change equal to that average rate. So let's say this is 1, 1, and this is 5, 7. So I'm going to take 7 minus 1 over 5 minus 1. So that guarantees me at some point I will have the slope 3 over 2. And so 3 over 2 kind of looks like this. And so I kind of see that possibly right there. So the mean value theorem just kind of helps us make sure that we have certain slopes on these intervals. And what we're going to do in class is we're going to kind of go over what we call the hypothesis and conclusion to help us with our AP questions. So for tomorrow, just make sure we can understand that my function needs to be continuous on a closed interval and differentiable on an open interval. And as long as I meet that hypothesis, I can make this conclusion. So let's say I had a cusp. If we look at our cusp on a closed interval, so this is continuous, but it's not differentiable. And so I cannot make that assumption. And then if I had a jump discontinuity, not continuous, and so I can't make that conclusion. So we're really going to be focusing on the hypothesis and conclusion and what type of functions we can assume this mean value theorem for. So this was a really long calc chat, but thank you for watching. Please come to class with any questions that you might have, and I look forward to doing this with you guys. Also, please like and subscribe to my videos and my channel. Thank you for watching.